All right, so this problem says one hazard of space travel is debris left by previous missions. There are several thousand objects orbiting Earth that are large enough to be detected by radar. So the US military, for instance, tracks every object bigger than a baseball. Okay, so imagine this. You you can keep track of baseball-sized objects 300 miles away and more. Okay. But there are far greater numbers of very small objects such as flakes of paint. Calculate the force exerted by a 0.1 milligram chip of paint that strikes a spacecraft window at a relative speed of 4 kilometers per second. Given the collision lasts that time, okay, it's roughly 60 nanoseconds. Okay, so here's the idea. Okay, if you shoot a piece of metal at me at 1,000 meters per second, a bullet, does that hurt? So here's a bullet that comes at 1,000 meters per second, that hurts. Okay, what if I keep a bullet stationary and shoot me at 1,000 meters per second to the bullet? Will it hurt the same, less, more? You guys understand the question? It'll hurt exactly the same. So here's a speck of stuff. If the space shuttle is going at 8 kilometers a second, or that speck is coming at 8 kilometers a second, the damage is the same. All right. All right, so calculate the force exerted on the 1 milligram chip of paint that strikes us. Okay. So so there's a small object, okay, and it's stopped by, it doesn't explicitly say that, but we'll say it's stopped by the window. To stop it, the force exerted on the speck was in this direction. So the force exerted on the paint was this, and the reaction force on the window was that. Okay. So the magnitude on the paint was the change in momentum of the paint divided by the time over which that change happened. Okay. What was the MV final minus MV initial, divided by the time over which that change happened? And the final velocity of the paint was 0, speck of paint was 0. So the force to stop that speck of paint exerted by the window was mass. Okay, the negative sign, we're just interested in the magnitude. The mass was 0.1 milligram. A milli is 10 to the minus 3, and a gram is 10 to the minus 3 kgs. Okay. Times the initial velocity. And the velocity is 4 into 10 to the 3 meters per second. And the collision time was 60 nanoseconds. All right, again, you want to take care of the powers of 10. That's 10 minus 6, and then that's 10 minus 3, 10 to the 5, and then there's a 1, so 10 to the minus 1, so that's 10 to the 4. 4/6 into 10 to the 4 newtons. Okay, 0.67 So the force on the speck of paint was 6.7 to the 3 newtons, and so the corresponding force was on the window was that. Okay, so 670 newtons is roughly the weight of a person. So that's the weight of 10 people. The force was the weight of 10 people. Again, now it's a speck of paint. Remember, a force, 10-pound force, this didn't hurt. But if the force is exerted on a small area, that can cause damage. So you see even little tiny specks of stuff because everything is moving fast. Okay, and the relative speed is what matters. Okay, so the space shuttle is moving this way, and if the speck is moving that way, that's dangerous. If they're both moving with the same speed in the same direction, then that's no problem. 2,000 kg railway freight car coasts at 4.4 meters per second underneath a grain terminal, which dumps grain directly down into the freight car. If the speed of the loaded freight car must not go below 3 meters per second, what is the maximum mass of grain it can accept? All right, so this is so here's a grain chute. So here's an empty car that comes in, and okay. So when the car is underneath the chute, grain is dumped in, and then this car keeps going. So you have to do this kind of stuff, when you have a lot of grain to load and that kind of stuff. All right, when the grain falls, the force of the grain is downwards, and that's balanced by the normal force. So external force on this guy is 0. Okay, so here is this initial momentum, and now the grain chute is empty, and the grain is in the car, and you want this guy to go at 3 meters per second. So here's the final momentum. Okay. All the forces that were acting on the system added up to 0. So final momentum, external forces added up to 0 should equal this. Okay. So 2,000 kgs. Okay. Times 4.4 meters should equal final mass times 3 meters per second. So final mass works out to okay, so how much grain can you put in? The grain is 933 kgs. Okay, so if you put more grain, then the car will be going slower and somebody will come and hit you from the back. And if you put less grain, it'll be going faster, and maybe somebody's not prepared to receive you yet. Okay. You're standing on a very slippery, icy surface and throw a 1 kg football horizontally at a speed of 6.7 meters per second. What is your velocity when you release the football? That's a heavy football. Anybody know the mass of a football? Okay, so your initial momentum is 0 for the system. Okay, so there's the final momentum. Zero equal to mass of football times velocity of football plus mass of person times recoil velocity. So about a tenth of a meter per second. The negative sign just telling you that you're going in the opposite direction, and that's your speed. Yep. All right, guys, we'll stop here.